Hello viewers, welcome to the next episode on periodic properties. In earlier episodes, we learned about the atomic size, ionization energy and electron affinity. In the electron affinity, we learned what is electron affinity and how this electron affinity is affected in the periodic table, and what are the factors which affect the value of electron affinity. In this present episode, we will learn about the trends in values of electron affinity in the periodic table. Then we will learn about the determination of electron affinity with the help of Born-Haber cycle, and after that we will learn about the electronegativity, the periodicity in periodic properties, particularly in respect to electronegativity. We will know about the determination and scale of electronegativity. So, this is our today's plan, and now we will go through a table. It is a graph which shows the variation in value of electron affinity with atomic number. In this graph, we see that the values of electron affinity, particularly these are the values which are peak of the halogens or 17th group elements. Here we find that all the halogens are present at the peak position, and here the value of chlorine is most. Chlorine is the element which has highest value of electron affinity. When an electron is added to the chlorine atom, maximum amount of energy is released, and that shows that it has the highest value of electron affinity. Then at the bottom we find here there are noble gases which have least value of electron affinity. Here we also find the second group elements, that is beryllium, magnesium. These elements also have low value of electron affinity because of their electronic configuration. In these elements, the NS shell is completely filled, therefore, they have least tendency to accept the electron, or rather we have to supply the energy if we have to add another electron in their valency shell. So, they have least value of electron affinity. Then zinc, cadmium and mercury, they also have very low value of electron affinity, because in these elements the penultimate shell as well as the outermost shell, S subshell, is completely filled. Therefore, they have very low value of electron affinity. Besides that, alkali metals also have a low value of electron affinity. So, they are also present nearly to the bottom of the peaks. Similarly, we can again go through this table to see the variation, and here also we find that the noble gases as well as the 15 group elements and second group elements, they have least value of electron affinity, and these values, when we move down the group, we find that the value of electron affinity is gradually decreasing. In first group also it is gradually decreasing. We have seen earlier also there was exception in the case of 15th group and 16th group element, as well as in 17th group elements. The value of next element, that is phosphorus, sulfur or chlorine, they have higher value than their previous element or the second row element, that is nitrogen, oxygen or fluorine. So, this is being the small size of these atoms, particularly nitrogen, oxygen or fluorine. When an extra electron is added to their outermost shell, there is a electron-electron repulsions. Due to this, they have least tendency to accept the electron, and they have very low value in comparison to next element. So, this is what we find in the case of values of electron affinities. Now, we have to find how these values of electron affinity can be determined. As such, it is very difficult to measure the amount of energy released when an electron is added to a neutral gaseous atom. It cannot be determined directly. Therefore, we have to find out the method, and with the help of Born-Haber cycle, we can find out the value of electron affinity. So, this is the indirect method to determine the values of electron affinity, and this Born-Haber cycle is a special case which is applied to the Hess's law. as we know that in Hess's law, the overall energy change in a process depends upon the energy of the initial and the final states only. It does not matter in how many steps the reaction has taken place. If we sum up all the steps involved in the reactions which is taking place in the multiple steps, we find that the initial values or overall change in values is same. So, with the help of Hess's law, we apply when it is applied to the Born-Haber cycle, we find that whether the reaction is taking place in a single step or it is taking place in a multiple step, the net change in energy is same. So, with its help we can determine the values of electron affinity. So, this Born-Haber cycle relates the lattice energy of a crystal to other thermodynamically data. It can be illustrated by taking energy terms involved in a formation of a crystal lattice of the sodium chloride. We know that the sodium chloride crystal is formed from the elemental states of the sodium atom and the chlorine atom. But when these atoms are present in solid state, then the heat of formation of the sodium chloride is determined. If we have to take the reactions in the multiple steps, then first we have to change the elemental sodium atom into the gaseous state, then it is changed into the ions, and similarly crystal is made up of by the electrostatic forces of the attraction exists between the ions. So, there are heat of or enthalpy of sublimations. Then in the case of chlorine atom, it is first we have to take the chlorine molecule, then we have to take the heat of dissociation for the chlorine molecule into atom, and then these chlorine molecule, when it changes into the chlorine atom or when the sodium atom changes into the gaseous sodium atom, then they are changes into the ions. Sodium atom has to lose the electron, and in losing the electron we have to supply the energy which is equal to its ionization energy. So, again this energy is supplied to the system, and then this chlorine atom, it gains the electron, and when it gains the electron then it releases the energy which is equal to its electron affinity. So, in this way these ions, when this chlorine atom changes into ion, that is anion, chloride ion, or sodium atom changes into the sodium ion, then electrostatic forces of attraction exist between these sodium ion and chloride ion to give 1 mole of the crystal of sodium, and in the formation of a 1 mole of the crystal of the sodium, some amount of energy is released. That amount of energy is known as lattice energy. So, in this way there are various thermodynamical terms which are used, that is heat of sublimation, heat of ionization, that is the ionization energy, then heat of dissociation of chlorine molecule into chlorine atom, then absorption, then release of energy in the form of electron affinity, and finally the lattice energy. So, all these various forms of energies are absorbed or evolved. So, all these forms of energies which are evolved or absorbed can be looked with the help of the Born-Haber cycle. So, this crystals is formed, then it is possible to calculate lattice energy, and then by substituting the values of all enthalpies in the equation, we can calculate the values of electron affinity. Now, in this equation we find that it is the delta HF, that is the heat of formation of a sodium chloride crystal from atomic sodium and chlorine atom. So, this heat of formation of a sodium chloride is equal to the heat of sublimation of the sodium chloride, then it is the ionization energy of the sodium gaseous sodium atom, then heat of dissociation of the chlorine molecule into chlorine atom, then electron affinity values, and finally, when these anion and cation unite to give a 1 mole of the sodium chloride, that is the lattice energy of the sodium chloride, heat of lattice energy. So, in this way, this whether the reaction is taking place in one step or here it is taking place in various steps, the net heat of or energy change will be the same. So, with this help we find out that heat of formation of a sodium chloride is minus 411 kilojoules per mole, whereas heat of sublimation of a sodium atom is 109, ionization energy of sodium atom is 449, then heat of dissociation of chlorine molecule is 121, then electron affinity, we have to find out the electron affinity. So, we will calculate it, and we know the lattice energy of the sodium chloride is 726 kilojoules per mole. So, by substituting these values, we can find out the electron affinity of a atom. So, in this way, the electron affinity of the chlorine atom we have to find out, and it is find out to be 364 kilojoules per mole. So, this is the way with the help of which we can find out the electron affinity of any atom. Or here in this cycle, if we go through this cycle, all the enthalpies changes, they are illustrated in this figure. Here we find that sodium atom is taken into the solid form, and it is 1/2 of the chlorine molecule, that is one chlorine atom we have taken here, it is in the gaseous form, and when they unite, they give rise to sodium chloride crystal, or it is solid. So, this is the heat of the formation of the sodium chloride. Here it is value is 411 kilojoules per mole. So, this is the single step reaction, and if we take the formation of this sodium chloride into multiple steps, then there will be various changes, and these enthalpies or the changes will be are noticed here. We can see them here. So, when this sodium atom, it is the heat of sublimation of the sodium atom into the gaseous ion, then this gaseous ion loses an electron, and here it is the amount of energy required to remove an electron, it changes into the sodium gaseous ion. And this chlorine molecule changes into the chlorine atom, and here it is the dissociation energy required for the one chlorine molecule to change into the chlorine atom. This gaseous ion, now when it gains an electron, the energy is released, and this amount of energy which is released here, we have to find out that. So, when these gaseous sodium ion and gaseous chloride ion unite to form a 1 mole of sodium chloride, in this formation of a 1 mole of the lattice, minus 726 kilojoules of energy is released, and this amount of energy is the lattice energy. So, we know the value of lattice energy of 1 mole of sodium chloride, we know the heat of dissociation of chlorine atom, we know the heat of sublimation of sodium atom, we know the ionization energy of the sodium atom. So, from these data we can calculate the electron affinity value. So, this electron affinity value can be known only by the indirect methods, and here by substituting these values in the equation, we get the net value, and that is the electron affinity of the chlorine is 364 kilojoules per mole. So, in this way we can calculate the values of electron affinity. So, these values cannot be determined directly, but these values are determined only by the indirect methods. Then another very important property which shows the periodicity for the atom is the electronegativity. And this electronegativity, we find that when these compounds are formed, or we find that the electrons shared between two atoms, it not evenly distributed if the two atoms are dissimilar or the molecule is heteronuclear. And we know that covalent bond is formed by the sharing of the electrons. So, when the electrons are shared between the two atoms, then a covalent bond is formed, and if the electrons are shared between the same atoms, that is the molecule is homonuclear molecule like hydrogen molecule H2, fluorine molecule F2, nitrogen molecule N2, chlorine Cl2. So, in these molecules, since the two atoms are similar, the electron pair which is shared between the two atoms lies exactly at the center or at the midway between the nuclei of the two atoms, because both the atoms have same attraction for the electrons, and since the electrons are same, so forces of attraction exerted by the nucleus on these shared electrons are also same. Therefore, the shared pair lie at the center of these two nuclei. There is no poles are formed, so molecule is said to be the non-polar. But when the covalent bond is formed between the two dissimilar atoms, then the electron pair may be closer to one of the two atoms because of force of attraction exerted by the nucleus. And now in this figure, if we see that this is the molecule, AB molecule, and they share the electron pair by forming a single covalent bond. So, depending on the force of the attraction exerted by the nucleus of either A or atom B, which atom has more forces of attraction towards this shared pair of electron, the shared pair of electron will shift towards that atom. And in this we find that this shared pair of electron is now shifted towards the atom B. It means the B has more attracting power than atom A. Since this electron pair is shifted towards the atom B, this atom B acquire a partial negative charge or delta negative, because of this electron pair is over the atom B, whereas there is a deficiency of electron around atom A. Therefore, this A atom acquire a partial positive charge. So, in this way we find that it is a tendency of a atom in a molecule to attract the shared pair of electron towards itself. Therefore, this B is said to be more electronegative than A, so that the bonded electron pair are attracted towards the atom B. Therefore, this electronegativity of an atom in a molecule is defined as a tendency of an atom in a molecule to attract the shared pair of electron towards itself. The different atoms in different molecules have different tendencies to attract the bonding electron pair towards themselves. So, this electronegativity is the property which is found in the molecules, whereas the properties like atomic size, ionization energy or electron affinity, these are the atomic property, but this property is a relative tendency of an atom in a molecule to attract the shared pair of electron. So, greater the ability of an atom to attract the shared pair, greater will be its electronegativity. And this is due to the fact that different atoms have different tendencies to attract the shared pair of electron towards itself. It must be remembered here that electronegativity is related to the atom bonded in a molecule, that is, it is a molecular property, while I have earlier said also that ionization energy and electron affinity are the atomic properties. This electronegativity is a relative tendency of an atom to attract the shared pair of electron towards itself, and it is generally denoted by the Greek letter chi. If the electronegativity of atom A is written as chi A. So, this chi A shows the electronegativity. If value of electronegativity of atom A is more, then the chi A value for atom A will be high. Then we have to determine the value of electronegativity, and this electronegativity cannot be determined directly, it is also determined indirectly, and as I have just explained that it is a relative tendency of an atom in a molecule. So, it cannot be determined directly. Number of scales have been proposed by different chemists and use different methods to measure or to estimate the value of electronegativity, because it is a relative tendency of an atom in a molecule to attract the shared pair, and since it is a relative tendency, therefore, it has no units. So, electronegativity has no units. So, some of the important methods which are used for its calculation are as follows. The first method is of Pauling's scale, and Linus Pauling in 1932 was first to propose the scale of electronegativity on the basis of bond energy of a covalent bond. Because what is the bond energy? It is the amount of energy required to break a bond between the two covalently bonded molecule. So, that is the bond energy, and according to Pauling, in a purely covalent bond, that is, if the bond is purely covalent, that is, it is a non-polar bond. then the bond energy of a molecule AB, that is EAB, is geometric mean of the bond energies of the molecules A2 and B2, because molecule AB is formed from the molecule A2 and B2. So, this bond energy of AB will be the geometric mean of the bond energies of the molecules A2 and B2. It can also be shown as that EAA, that is the bond energy of molecule A, and EBB is the bond energy of the molecule B2. So, this is equal to, that is the bond energy of molecule AB, that is the EAB is equal to product of the bond energies of molecule A2, that is EAA, and E product of the molecule of bond energy of B2, that is EB2, and it is the under root of these values. So, this above relation is based on the assumption that the bonds in molecule AB, A2 and B2 are purely covalent. Purely covalent means that the shared pair of electron is present at the center of the nuclei A and B in case of molecule AB, as it will be present at the center in case of A2 or B2. So, Pauling observed that in most of the heteronuclear bonds of type AB, the bonds has partial ionic character. Earlier we were considering as purely covalent bond, but he observed that if the molecule says heteronuclear, that is AB type, then he observed that bond has partial ionic character, and due to this partial ionic character, the AB bond is stronger than the pure covalent bond, because here if the bond has partial ionic character, so due to electrostatic forces of attraction, that bonds become stronger than the purely covalent bond, and this extra bond energy is shown by delta E. So, this delta E, that is the extra bond energy, will be equal to the actual bond energy minus bond energy of the pure covalent bond, or this is delta E is equal to E AB minus under root of the product of the bond energies of A2 and B2. So, delta E is the extra bond energy, and this measures the polarity of the bond AB, which depends upon the electronegativities of the atom A and atom B, that is chi A and chi B respectively. So, this extra bond energies shows the electronegativities of the atom A and B. By calculating the delta E for different bonds, Pauling proposed the following empirical expression to correlate the extra bond energy, that is bond energy, with electronegativity difference of the two atoms chi A and chi B. That is the difference in the electronegativity of the two, chi A minus chi B is equal to 0.18 into square root of the change in bond energy, that is delta E. Or we can simply say that chi A minus chi B is equal to 0.18 into under root of delta E, where delta E is the excess bond energies in kilocalories per mole. So, Pauli assigned an arbitrary chi values of 2.1 for hydrogen and calculated the electronegativity values of elements from carbon to fluorine in the range of 2.5 to 4. So, arbitrarily he assigned a value of 2.1 for hydrogen atom, and by substituting these values from carbon to fluorine in the above equation, he find that the values of these carbon, nitrogen, oxygen and fluorine ranges in between 2.5 to 4. Then another scale is the Mulliken's scale. In 1934, Mulliken proposed a new scale to determine the values of electronegativity, and according to Mulliken, electronegativity of an element is the arithmetic mean of its ionization energy and electron affinity. Thus, electronegativity is equal to, it is the mean of ionization energy and electron affinity, that is ionization energy plus electron affinity by 2. So, it is a very simple formula to know the value of electronegativity, with the help of electron affinity and ionization energies. The main disadvantage of this Mulliken scale are that electron affinity of values of only few elements are known, and whereas second disadvantage is that ionization energy and electron affinity values changes with the valency state of the elements. So, here we conclude that in the present lessons we learn about the determination of electron affinity and the periodic trends observed in the electron affinity. Also, we learned about the electronegativity, how we can define the electronegativity, and from the Pauling scales we find out that the fluorine is the most electronegative element and it is assigned a value 4. So, two scales we have learned, that Pauling scale and Mulliken scale. In next lecture we will discuss about the trends in electronegativity in the periodic table, then applications of the electronegativity and how these various properties varies in the periodic table, or how these all atomic properties